time we introduced friction, and we start talking about an object that was on the floor, and you were pushing this object. Someone was pushing on the object with some force, and the object then started to resist the motion with some force of friction. Now we said that as long as the object is not moving, so as long as it's not moving, then we are talking about static friction. Static friction. And now let me introduce how we calculate friction. Static friction, by the way, will increase to resist your force that you're applying here, F. Let's call this F, the force that we're applying. Static friction, I'll put sub S for static. Static friction will be equal and opposite to the force you apply to resist the motion, because we have equilibrium, right? The reason the object's not moving is if I apply 5 newtons this way and friction applies 5 newtons that way, then nothing happens because the two vectors cancel each other out. All right, and there's no motion. So as long as the box isn't moving and you're not budging it, so as to say, the force of friction has to be equal and opposite to the force that you're going to apply. So that's what static friction does, and it will track one for one what force you apply up until some maximum value. And then beyond the maximum value, it can't take it anymore, and you will overcome friction and you will start to push the box, and the box will move. So the force of friction, static, maximum, is going to be equal to this coefficient mu sub static, and I'll explain that in a minute, times the normal force. N is the normal force. All right? So the maximum force of friction, static friction that is, that's going to be able to resist you, is equal to the coefficient of static friction times the normal force. This coefficient of static friction has to do with the two surfaces that are coming in contact with each other, and you could look these values up. They're constant numbers, less than 1, and you could look them up in a table for, let's say, wood to glass, wood to wood, steel to, I don't know, iron, whatever. Any two surfaces that can come into contact, they have different coefficient of static friction. They're always less than 1. And this is what's important here, is the normal force. So let's review what this normal force is. If I have a box here and it's sitting on the floor, I have the force of gravity here, which is its weight. And then I have the force of the floor pushing up on the box, and we call that the normal force. Normal because it's perpendicular. Normal is another word to use to describe this concept of being perpendicular. And it's normal to the surface that your object's sitting or resting on. So it's always straight up in that direction like that. So this is the normal force here, and if you take this quantity and plug it in there, you will understand and get the maximum force of static friction that the box will exert, let's say in this direction, if you start to apply a force in that direction. So the force of friction then is completely dependent on this normal force. Okay? Now what happens is once the box starts to move, static friction is no longer coming into play because there's nothing stationary or static. It's not at rest now. It's finally moving, and something different comes into play. The box is now moving. We're pushing it with a force, and now we have a force of friction resisting it, but now it's kinetic friction. It's friction of motion, and this is equal to the mu sub kinetic, which is a different coefficient than our static coefficient, again depending on the two surfaces in contact with each other. This is the coefficient, it's just a number, coefficient of kinetic friction times the normal force. So in either case, the forces of friction, whether it's kinetic friction or stationary or static friction, they depend on that normal force. All right, so if you can reduce the normal force, then you reduce the force of friction. And we're going to take an example now of how that goes, and we'll continue it in the next video, but let me just do this, start it for us so we could see what's going on. Okay, so let's take an example here. Let's say we've got a box here and it's sitting on the floor, and the box weighs 10 kilograms. Then what are the forces? Let's do the free body diagram. We have the force of its weight. The weight is equal to the force due to gravity, and that will be the mass times the acceleration due to gravity, and this g is 9.8 meters per second squared. So the force of gravity, which is equal to its weight, is equal to 10 kilograms times 9.8 meters per second squared. And if we do that, let's just assume this is, okay, so let's say this is then going to be 98 newtons. All right, so let's say it's 98 newtons down. And if it's not moving off the floor or not going through the floor, then we know that the floor has to then exert an upward force of 9.8 newtons up. This is the normal force. So in the case of something that's flat on the ground, the normal force is going to be equal to its weight. We're going to see in the next video what happens when we raise the ground at some angle and the box is sitting like this on the ground, and we're going to see what happens to this blue normal force right here. What do you think is going to happen to it? Well, I'm going to give you a clue. This guy here is going to become less than 9.8. In fact, as you raise your platform up through an angle, this normal force is going to start to go down and get smaller and smaller and smaller until it becomes so small that the force of friction is too small and the box will start to slide down the plane. So we'll discuss this type of thing in the next video.